Okay, well, good afternoon. We're going to review the last few lectures of this course, and then we'll finish off by talking a little bit about the assignments and labs, and we'll ask any questions about the final exam. So as I've been doing for the last 2 times we've met, I'm just reviewing the course at a high level, using this as a way of walking through the sections and flagging the parts that I think are most important, and what I'm going to encourage you to review before the final exam. As before, go ahead, turn on your microphone if you got one, or enter the chat. Ask me questions as we go through this. I've already gone and I've taken the last sort of 5 lectures and condensed it down to a single notebook and pushed that already to your account if you want to see it. In lecture 14, we talked about SymPy. So SymPy is a different kind of tool than numerically analyzing this kind of stuff. So I've reduced it down to the what I'm going to call the bare essentials. So in terms of SymPy, being able to understand how to define symbols, important. Being able to take those symbols and build up expressions, important. Being able to take the derivative of an expression, useful. And simplify those expressions. One of the things we saw is when you have expressions, what you can do is you can evaluate it purely symbolically. So if you have something like the sine of x, that's an expression, right? It's a mathematical thing. We can substitute in numerical values. We can say x equals 0, substitute that in, sine of 0 is 0. Substituting in x equals minus 1, well, for Arctos, you get pi as the answer. These are exact symbolic answers. If you wanted a numerical representation, this is where eval f, eval floating point. And the n is how many significant digits we want. This is how you evaluate expressions for single points. If you want to evaluate it for lots of points, we can take any SymPy expression and turn it into a function, a Python function. And the way we do this is we use something called lambdify. And the idea of lambdify is to take a function, like here is an example of a function. My func is the function that takes x and returns back 2 times x. So that's a function. To lambdify something, what you do is you take the arguments, everything that goes into the function, and you give it the expression, what the function represents, and what it gives you back is a function. And one of the things we saw in some of the labs and assignments is lambdify can take many arguments. It can not just take x, but it could take x1, x2, y1, y2, all the way through. These lambdifications are useful for setting up a problem numerically or symbolically, so you can then solve it numerically. We talked a little bit about solving equations, and the important takeaway here for SymPy is you can't set up an equation by saying x squared equals y. Equals is already reserved for assignment in Python. So there's 2 structures. One is to either use inequality expression, basically saying this thing is equal to this thing. It's one way of doing it. And that allows you to talk about the left-hand side of the equation or the right-hand side of the equation. The other way of doing this kind of construction is whenever you're solving an equation, if there isn't a right-hand side, if it's just an expression, you assume the expression is equal to 0, and that's the equation you're going to be solving. So with those 2 different ways of doing it, we talked about how to set these things up. And of course, in general, what you do is you have some set of symbols. You define an equation, and again, you can either define an equation as a single expression, v minus 4/3 pi r cubed, which you assume that's equal to 0, or you can use the equal operator and say this whole thing represents an equation. They're the same. The point is you take that expression and you pass it through something like solve, and you get back out the answers. Well, for this particular problem, the equation v equals 4/3 pi r cubed, if you're solving this equation for r, one of the solutions is r is the cube root of v. SymPy does all the mathematical solutions. R could be imaginary. We ignore those 2 because we know that for the volume of the sphere, we want real, not imaginary radii. So we pick just the first solution, and then we can substitute that in. So that's something we covered in terms of how to use these tools. And the final thing we did with SymPy was we can use SymPy to solve some differential equations. And the way we solve a differential equation is if you have a differential equation. So there is a classic differential equation. The derivative of some function is equal to a constant times itself. In SymPy's language, we define the symbols. You always need to define the symbols when you're dealing with SymPy. So T and A are just some mathematical things. F is this kind of symbol, but it's special. We're telling SymPy that it's a function. Once you have that, you can, well, I guess I should import the whole library. I won't worry about that. You can solve that by setting up an equation. And if you notice what I've got is I've got the derivative of f minus a times f. I'm actually writing out f of t and f of t because you got to know what you're taking the function evaluated at some point. This is an equation. It's got a minus sign because I moved everything over to the left-hand side and set the equation equal to 0. And I'm solving for f of t. So the solution to this differential equation is a constant e to the power of at. If you had a more complicated equation, you could set that up. Here's a more complicated equation. So the equation would be the derivative of f minus f times 1 minus f, solving for f. If you had initial conditions, like in lecture 13, we had this differential equation. Well, this differential equation is a mass times an acceleration is equal to minus b times a velocity minus m times g. M, b, and g, and there's also a time always buried in here, are the symbols. Y is the function. The second derivative of y is acceleration. The first derivative of y is the velocity. So we can write this whole thing as an equation. The equation is m times the second derivative of y is equal to minus the velocity minus m times g. You can solve these things using dsolve for some but not all differential equations. And then what we can do is substitute in initial conditions. Initial conditions are just values that you want to substitute in. Whatever you want to replace it. So if I want to replace y of t when t is equal to 0 with a constant y0, or I want to replace the derivative of y with respect to t when t is equal to 0 with v0, that's an example of initial conditions. You can take initial conditions and substitute that in. So that's how we use this to solve symbolic notation. So that's the set of things from SymPy. SymPy can do a lot more, but these are the constructs or the syntax or the ideas that we've reused in other parts of the course. So that's sort of condensed down into a couple pages. Is there anything about how SymPy is being used that we should discuss?
Dr. Munroe?
Yes, Kayla.
So just to be clear, for example, the equation that you gave with MA is equal to, what was it? Could you just scroll down to that equation,
Yeah,
please?
of course I can. So you mean the differential equation?
Yes, I do.
Okay. You are talking about this one.
Yes, I am.
Okay.
So just to clarify, SymPy, we're supposed to use SymPy in a way that we are constructing differential equations, so to speak, or deriving
Right.
differential equations?
So, or algebraic equations.
Oh, okay.
Right. So what SymPy is giving you is a tool
Yes.
to solve any differential equation that you would know how to if you had taken a second or year course in ordinary differential equations.
Oh, okay.
Using
All
the
right.
techniques that you do them by hand. It can't solve everything. It can
Okay.
solve a number of types of differential equations. Like if you've taken differential equations, you've learned about integrating factors
Yes.
and separation of variables and
Yep.
like these different techniques. It knows
Yes.
how to do those techniques.
Oh, okay.
But not all differential equations can be solved analytically.
Yes, that's true.
Right. So if it's one that's in the standard textbooks, SymPy can do
Then
it. And what's nice about it is you write down the differential equation, and even though that might not be, this is a second order differential equation with constant coefficients. right?
Yes.
The actual arithmetic or the algebra in figuring out what all the constants are, there's lots of opportunities to make a mistake here.
Mm-hmm.
And what SymPy is doing for you is abstracting out the idea of solving from the details of what actually the answer is.
Oh, okay.
Right.
All right. I
Um,
understand.
okay, so that's why this tool exists at all,
Oh, okay.
as a thing. Okay, so that's SymPy. Then I gave you a number of examples of how one could use SymPy to solve slightly harder mechanics problems, all symbolically. So what I've done is I've taken lecture 15, and I had like 10 examples in this lecture, and I've just reduced it down. I deleted examples that I don't think are worth studying, and I've left in about half the examples that I think are worth taking a look at. So just to reduce this lecture down. So for example, the physical problem of how would I solve the motion of a block on an inclined plane where there's a static friction, and I'm lifting it up. So this is a problem you can solve with pen and paper, but this is how it would be solved in the SymPy framework. You're still having to talk about a free body diagram. You still need to talk about the forces, the components. You can write them all up. And what we're doing is we're constructing an equation. At the end of the day, there's going to be some equation. If it's in equilibrium, the sum of the forces equals 0. And I'm solving that system of equations for when to solve for the angle at which we're no longer in equilibrium. If I've got an inclined plane that I raise up to a certain angle, at some point, the forces are not going to be equilibrium anymore, and a block on that inclined plane is going to begin to accelerate. So that's the condition we're solving for. So this is a way of coming up with that critical angle. That's a generic symbolic formula. Then you can substitute in specific values of, say, the coefficient of static friction to get an actual number. So this is one of the ways of using it. Then we use that as a motivating problem, and now we do a problem which is harder to do with pen and paper. And this is the idea that you're raising up a inclined plane, but you're continuing to lift the inclined plane, making it steeper and steeper as you go. So you're raising it at an angular rate. You're raising it up at 0.4 radians per second. How does the block sliding down that plane behave? And the trick is there's an additional force. From the point of view of being in a reference frame relative to the inclined plane, there's a centrifugal force. There's something that's going to keep you rotating around in a circle. That force gets added in to the system of equations. That is your equation that you're going to solve for. You're going to solve for when those three forces are equal to 0, and it gives you a slightly more complicated solution. And again, there's an example of doing it. So there are two examples of doing a SymPy thing. And the other two problem I left on here was how you would do collisions in 1D. So this is something which we did in first year physics. You can do with pen and paper. Here is an equation. It's a conservation momentum equation. It's got lots of variables, M1, M2, V1, V1 final, V2, V2 final. So we define all the symbols. We define an equation. And then I can do things with this equation. So not only do you have conservation of momentum in a collision, but you may have conservation of energy if it's a perfectly elastic equation. Here's how I can solve a pair of equations, an equation for momentum, an equation for energy, for the velocities v1f and v2f. That will solve these pair of equations, conservation of energy, conservation of momentum, this equation, and this equation, for the variables v1f and v2f. In terms of all the other variables, right? You can solve this system of equation for any two variables you like. You could solve it in terms of mass 1 and mass 2 if you wanted. You can solve it for any combination. Only two variables because there's two equations. This system has two solutions. One is two objects have the same final velocity as their initial velocity. That just means the objects did not bump into each other. There was no collision. The other one is the one we're searching for. This is the one where two objects of different masses collide with each other, exchange momentum, exchange energy. And this is the one we may want to look at. So this is the kind of thing we did in first year physics, and you can do that problem. Where SymPy comes into the strength in this course is being able to set up the modeling of not just before the collision and after the collision, but during the collision. If you want to model the speed of the two particles as they're hitting each other, two carts on a track, as they're colliding, this is something we did not do in first year physics, but the actual, how long did it take them to collide? What was the nature of the reaction? Well, there we'd set up a system of equations. It's still, we still need to have some interaction between those two things. So there could be a force, it could be a magnetic force, a gravitational force, an electrostatic force, or some other force as given right here. So here is a force dependent on the position of the two carts. I don't know what kind of forces between them, but let's just say that the force acting on these two carts is dependent on how far away they are from each other, right? If that's the force, then this becomes an equation of motion, okay? Mass times acceleration is equal to the net force on the object. This is something that cannot be solved symbolically. I don't have a method with pen and paper for solving the second derivative of something divided by x minus x2 to the power of 4. There are a coupled set of equations. However, what we can do is we can take this system of equations and use it to help us write down a numerical solver. So you can use this structure, this way of writing it down, to help us understand or build the right-hand side of the dynamical system. The idea being, in all these dynamical systems, we're talking about the derivative of something with respect to time equals some function. What you put right here might be complicated, and it might require some algebra or calculus or derivatives to get to this point. Using SymPy can be helpful in doing that. So this is something we've seen on the labs and the assignments. The force might be dependent on a potential. So you may need to take the derivative of something to figure out what this is, this expression needs to be. If you have an expression, you can put it to the right-hand side of something and implement some solver. ODE int is a built-in solver. You can use Runge-Kutta order 4, you could use midpoint scheme, you could use Euler, you could use any one of a number of different solvers. So this is an example of a collision. Two particles started off at these two locations. As they traveled, one was moving towards the left, the x-coordinate is decreasing, one's moving towards the right. They collide. Now, the modeling of this collision is they don't need to touch. Their forces go to be repulsive, and they bounce off of each other. What we're modeling is the interaction between those two things. So I'm putting collide in quotes because they're not actually touching, but it's still a collision from a force point of view. And now we're able to see not only what the initial and final velocities are, but actually how the velocity changed all the way through. This is the idea of numerical modeling. Finally, the last example I'll leave in here is a more complicated problem of a falling rope. So this is the idea that you've got a rope which is coiled up on the top of a platform or a table, and it's falling. This is the equation of motion. It's a problem where the mass of the rope is actually increasing with time as more of it unspools and falls over. So here's something that we can write down the equation symbolically and use that to come up with and manipulate this to figure out what this actually should be written as, what the net force is on the thing, to come up with the equation of motion. We're using SymPy to manipulate this equation, so we actually have an equation that needs to be solved. And here we go. After manipulating it, this is the equation. Y and V are the variables. V is just the derivative of Y. This is the equation we want to solve. So if I rewrite this equation as the derivative of V equals something, and the derivative of Y equals something, that's a pair of equations written in the form of derivatives equals stuff. That stuff is the right-hand side. So what I can do is I can turn the solution of this equation into a function using lambda-phi, and that function can be substituted in, and we solve it in a system like this. This is the right-hand side. So once we've defined that function, we can substitute that in. This idea is what you did on the last lab, and you're doing on the last assignment right now. This is an important idea. Okay, so that's the SymPy stuff. Anything else on the SymPy things we should talk about? And I would say that this example, along with assignment 7 and lab 7, is the same idea, right? We could have a different problem, but that idea of manipulating it, constructing a function, and then passing it through some solver, that's an idea we've seen 3 or 4 times now. Does anyone have any questions about that? Okay. Once we did this stuff on SymPy, we spent a week doing a geophysics application. We talked about travel times of seismic waves. This is a really simple thing for preparing for the exam. There you go. I've reduced the lectures down to the bare essentials. This is what you need to know. Nothing. It's a worked example. It's neat, it's interesting, I like it, but there's nothing in those lectures that by itself I'm going to test you on or evaluate on. You've completed a lab on it. You've looked at it. You attended the lecture. We're done. I think it is perfectly safe for you just to skip over lectures 16 and 17 entirely. There will not be a question on ray tracing equations or Snell's law or polar coordinate representation of things on the final exam. So is there anything from lecture 16 or 17, this stuff about earthquakes and travel time and seismology, that anyone wants to ask about though? Okay. And the last topic we covered in this course is we did a little bit of stuff on planetary motion, specifically on the 2-body and 3-body problem, Newton's law of gravity. So to remind you, Newton's law of gravity is 2 masses together divided by r squared, the distance between them. We often rewrite this unit vector for r. A vector represents the direction. We rewrite that as the actual vector between the 2 bodies divided by r itself. This is still an over r squared relationship. This is the force between any 2 things in a gravitational system. This value g, the gravitational constant, in SI units, the International System of Units, is a very small number. When we're dealing with planetary motion, we rewrite this in astronomical units. AU cubed divided by year squared, right? In those years, this number turns out to be mathematically 4 times pi squared, written in astronomical units. Some of the conservation laws about this system are angular momentum is conserved and total energy is conserved. It has to be. It has to be if the system is making any sense. These are the things that you could plot as diagnostics to check whether or not you're solving the problem already. We did not do an example in lecture of actually showing what the energy of a planet would be as it went around. We did not do an example in lecture of what the momentum of a pair of planets would be as they went around. But these are oscillatory systems. We did talk about how to look at diagnostics like energy and momentum for oscillatory systems like pendulums. You do know from first-year physics that momentum is conserved and energy is conserved. So it would be entirely reasonable for me to construct a question that sets up the equations of motion for 2 objects in a gravitational field and do something that involves you having to understand what the plot of either this or this should tell you. Now, I would give you what this is, I would give you what this is. Now I could give it to you in steps. I could say, what's the kinetic energy? What's the potential? What's the total energy? Write down the line of code that plots the total energy versus time. Here's the plot. What does that tell you about the stability of the solution? And the answer is, if the number is constant, it's stable. And if the numbers are not constant, if they're growing with time, the numerical scheme is unstable. Okay, so that's how you bring these ideas together. So I'm going to leave this here, even though we didn't do an explicit example, it follows naturally from other things we've done in the course. Okay, so for this particular example, if you have a single mass rotating around a massive star, that's the system of equations, left-hand side, right-hand side. Here is how we would solve that system with an RK4 stepper. So this is taking that numerical algorithm, encoding up what the derivatives are, and then showing you an example of how to plot it. Putting all that together, we can build an application. Applications require initial conditions, parameters, some numerical method, and then we get the data back out. Just an orbiting planet. We can make this more complicated by looking at multiple objects, so mass 1 and mass 2. And so now there's going to be a pairwise force between any two masses. So when doing this in terms of forces, we just say the mass times the acceleration of the first object has the force of the sun on mass 1 and the force of gravity of mass 2 on mass 1. The equation of motion for object number 2, mass times acceleration, is equal to the force of the gravity of the sun on mass 2 and the force of gravity of mass 1 on mass 2. And because of Newton's third law, these two forces are equal and opposite. If we wanted to make this a 3-mass system and explicitly model the motion of the sun, we would have a third equation. Mass of the sun equals the acceleration of the sun equals the force of gravity of this planet, m1 on the sun, plus the force of gravity of this planet on the sun. And that would make it a 3-body problem, or a 4-body problem, or a 5-body problem, as many as you want. And we can extend this up to an n-body problem. When there are more variables, the state becomes more complicated. In this problem, because we're going to assume the sun is so massive that it doesn't need to move, we've got coordinates in state and phase space of x1, y1, vx1, vy1 for the first particle, and another set of 4 for the second particle. And on the assignment, we did this for a third particle, right? So it just keeps on growing all the way through. Here is what the right-hand side equation is. Okay, there's the state vector. There's the parameters. There's some work that we're doing in the middle to calculate the distance between them. Those are things that we can calculate it. And here are the derivatives. This stuff, these 8 lines, what they are is these right-hand sides. Okay, remember this is the derivative of acceleration, or the derivative of, the derivative of velocity, the second derivative of position, in 2 coordinates. There's a coordinate for x and a coordinate for y. And when we take these second-order differential equations, we turn them into a pair of first-order equations. So these 2 equations, when written out, become 8 equations. If we've got those equations, we can stick those into an application, state vector, parameters, stepper, solve it. When we solve it, we can plot it. Okay, so that was the stuff we did on motion. So the idea is working with multiple particles all together. I do want to review the labs and the assignments in a moment, but is there anything else on this planetary motion 2-body, 3-body material that we should discuss? Okay then. So I said, I've already posted that lecture up there. I'll do this. Oh, hold on. How to know what the sign of each force has. Okay, so this is just a free body diagram, right? So you remember how we spent all this time in first year physics drawing free body diagrams? You put arrows on the objects, and the arrow needs to point in the right direction. That's what sets the direction. Gravitational forces are always attractive. That means they point towards the thing. If you're having a hard time in like when you're doing these kind of problems, trying to figure it out, you can always put some test data in. If you have two particles, the forces should be pointing in opposite directions. But really, to figure this kind of stuff out, you'd write it down, you draw it, you draw arrows, you try and figure out which force is to the right, which force is to the left. And it all depends on what the force is actually involved, because gravity is just one kind of force. There's lots of kinds of forces in the world. And those forces need to have the right direction, and the direction depends upon the sign. So, okay. How do you know which sign is setting up for a three-body problem, right? So, again, this force, F, is the force of one object on another. Newton's third law says that for every force there's an equal and opposite force. So think about all the forces acting on one object. Like if you have three objects, pick one and try and think about all the forces which are pushing or pulling on that object. Are they pushing to the right or to the left? Are they pushing to the right? It's a positive force. If it's pushing to the left, it's a negative force. For x coordinates. If it's pushing up, it's a positive force. If it's pushing down, it's a negative force for the vertical coordinate. Away or to forth. That's sort of how to think about it. Generally, negative forces are attractive. Positive forces are repulsive. Okay. Chat question number 2. In relation to the assignment, does this mean that it follows the same format as the three-body problem? Yes, the assignment 7, the question you're working on, is a three-body problem. It's got 3 equations. 3 mass times acceleration equals the net force. The net force is given by the force of the other 2 objects added together as a net force becomes the net force on the first object. You can write it up lots of different ways, but you can think about it as a set of 3 equations. Okay, so this is for 2. I'll go here. Here's for 2. In assignment number 7, you have 3 objects, 3 equations. Each equation is going to have 2 forces. The force of for particle number 1, the force of 2 on 1, the force of 3 on 1. For particle number 2, it's the force of 1 on 2 and 3 on 2. For particle number 3, it's the force of 1 on 3 and the force of 2 on 3. Okay, so that's the structure. Andrew, would the difficulty of the assignment question be similar to the question on the final? Maybe. Entirely possibly. In my mind, I have a 2-body problem as opposed to a 3-body problem. But that idea of having some force, which may not be gravity, it could be some other force, is entirely possible. It may use different language. It won't have a G in it, some other constant. But the idea of setting up the system of equations, being able to recognize going from that system of equations to something like this and filling in those details, and then knowing, whoa, don't cancel. And then knowing what goes here, goes here, goes here, goes here. That's really what I want to make sure you need to know how to do. There's a question in the chat that asks me, in F planet, what is the purpose of dx and dy? Okay, let's go back to the setup, right? These notebooks are not just the code. The code is only the implementation. This stuff, all this text, is really important in understanding the problems. And what it says is R21 is the difference between R2 and R1. R2 and R1 are position vectors. They're the coordinates, x1, y1, x1, y1, x2, y2. The difference between these two vectors is x2 minus x1, y2 minus y1. R21 is not an explicit variable. This is not a brand new variable. Once you know the direct how far away R1 is, a planet is from the sun, another planet is from the sun, you automatically know how far away the two planets are from each other. It's just a subtraction. So what we're doing is once we know where the two planets are, if I want to know how far away each planet is from each other, I just take their positions, x1, y1, and x2, y2, and construct the distance formula. So dx, dy are just the distances between the two particles. So dr, this is just the length of the vector r1, 2. So if you wanted, you could call it that. And that would be totally fine. That's the distance between those two things. Think about it as a triangle, draw out some position vectors. That's all we're dealing with here. Question. Do you need to find the net force before you apply A equals F over M, or can you do it component-wise? Never mind. Yes? I think the answer is yes to that.
Dr. Munroe,
Yes.
for that same part of the implementation, for the derivative, so still thinking about the assignment, is it that we use the midpoint stepper in this derivative? As in, I still wasn't clear on how to incorporate
when you're setting up the problem,
yes.
the numerical method, midpoint stepper, or K4, Euler, or Lacroix, none of that matters.
Okay.
Okay. So this is purely a physics problem that we're writing down.
Okay.
Okay. So we're trying to write down the problem in terms of derivatives.
Okay.
And the derivatives in this course have almost always been F equals ma. That's the equation.
Yes.
All the time. So we're writing down how the acceleration depends upon the sum of the forces. Okay. That's the system of equation that we've been solving again and again and again.
Yes.
Once you have that system of equations, it stops being a physics problem and it starts being a numerical question, a math question, basically. It's like, okay, I've got some variables. There are techniques to solve those systems of equations, and those are the different numerical methods.
Oh.
Right? So,
okay.
So what we've done is we said, and this is part of the theme, is we recognize that all these problems are a second derivative is equal to stuff. Okay?
Yes.
All this stuff is what the derivative is. Rather than having it being a specific form, we just say, okay, it's a generalized function. It's telling you what the derivative actually is. And the numerical methods are written in terms of the derivatives.
Okay.
Allowing us to solve all sorts of dynamical systems with the same numerical code.
Oh, okay. All right.
But that's what we took a whole course to work up to that, right? So there's a lot of examples where we solved it for lots of specific examples. And it's only at the end of the course we're able to say, actually, all those times we implemented Euler method or midpoint method, you can just have to do it once in your life and you're done.
Okay.
But
all right.
But it's got two different ideas all the way through. Okay. This is good. These are good questions. I like this. Okay to move on to the labs and assignments? Okay. I will post these up just in a moment as soon as we're done. But what I did is the same thing. I just took all the labs and threw them into one notebook. And I've kept the parts that I think are worth reviewing. I'm now up to the point where all the labs have been marked and returned and the solutions posted. So here we go. Here are the 7 labs. At the very beginning of the course, we talked about modeling drag on a guy jumping out of an airplane. So here was how we did that. The details are good to review, but here was the kind of problem. Imagine that you had some force that was being modeled as if it was a hyperbolic tangent. Okay, this is an empirical model. How do we construct empirical models? How do we make plots of things? Here is an example of a function which I could define as a NumPy function, right? It's more complicated looking, but it's basically a tanh and a constant and a 2 and a constant and a constant and a constant and a constant. Well, how did we define this as a function? How do we use these kind of functions to solve the motion of a problem that looks like this? This is acceleration is equal to the force of gravity per unit mass, mg divided by m, and the drag force per unit mass. Well, we can rewrite that as a pair of equations. Can you take that and can you implement something like Euler method? That's how we started the very first lab, this idea going the way through. So I think that's an important lab to at least go through and be like, yeah, I understand how that all works. Lab number 2, we looked at the example of a spinning basketball and this force which is at the angle to the right. I don't think there's anything particular about that lab that requires review. I am totally fine if you just skip right over it for the purposes of studying. We talked over pendulums. Pendulums, now we're talking about an oscillatory system. So here's a system of equations. This is a non-linear pendulum. It's non-linear because it doesn't depend upon theta, it depends upon the sine of theta. So it's a more complicated equation. Can you take this equation, split it up into 2 equations? Can you write down for any of the 3 numerical methods we've looked at, Euler, okay, 4, Euler, Euler-Kromer, midpoint rule, which is the same as Euler-Richardson, or Runge-Kutta order 4, can you write down, well, what goes here? What's the stuff which you would put to implement this model? And do you understand that what we're doing is we're solving it? Okay. Now, this particular one was also a way of talking about more complicated nonlinear phenomena, and it talked about finding peaks or finding periods. I think that was a neat application. I'm not overly. I don't think it's overly important about finding peaks on a final exam. So I'm just actually going to get rid of that so we don't confuse things at all. Will the interactive function be on the final? No. It makes no sense to have an interactive widget on a pen and paper exam. There's nothing to interact with. It'll just be straight plots, and I'll always plot it for you all the way through. Right, so here's the code for the nonlinear behavior. Let's read the entirely. Nonlinear behavior, and of course the one change is you have to figure out what you need to do these 2 pieces of code. Make sure you understand that. I'm going to get rid of this, rid of this, rid of this. The idea of phase plots is important to review. A phase plot, instead of plotting position versus time or velocity versus time, you can plot the variables against themselves, position versus velocity, or any other 2 variables in the system against each other. It's another way of describing what the problem does, and it gives you another way of looking at the behavior of the system. Know what a phase plot is. Okay, lab number 4 talked about numerical differentiation integration. So I'll leave this here as an example to review. Be able to take a line of code mathematically and give me back a Python function that implements it. Be able to come up with a derivative of it. Now, in this lab, I had you do it by hand. I'll put this here. Or with SymPy, okay? Because now we know about SymPy. So could you evaluate this function with SymPy? Would you know how to do that with some function? Could you teach SymPy how to take this derivative and construct a function, dgdx, that implemented it, right? That would be something which we didn't do in lab number 4 because we hadn't learned about it yet, but we know now. Once you have these functions, you can also differentiate things numerically. So that's differentiating something symbolically. We had these different schemes of differentiating things numerically. Review that. I'll leave this here. This idea of error is a good one. The idea that these numerical methods scale and have a certain order. And one way of talking about the order is how the error depends upon the size of the step. If the error decreases linearly with the size of the step, we call it a first order method. If it decreases quadratically with the size of the step, we call it a second order method, and so on and so forth. Not only do we need to be able to integrate and differentiate functions symbolic from expressions, we need to be able to do it if it's based on data. So imagine you've got some data, T versus V versus T data in a table. Can you apply these forward, centered, backward difference of functions and plot it? Can you numerically integrate those things? Trapezoid rule and rectangular rule all the way through. So I think that's pretty good for lab number 4. And for lab 5, this idea of how do I take data from the disk? And we were dealing with comma-separated values. How do I take that and load it up into a data frame? How do I make plots? How do I use polyfit? And how do I use, and I'm going to make this explicit because not everyone did it, using NP polyval, right? This is something we talked about. How do you take data in a table and come up with a best fit line of it? That's an important thing. In this particular lab, it's only this first part, part 1. Part 2 was on optimized curve fit, which we're not going to have in the final exam. Lab 6 was on earthquake detection. Again, don't worry about that one. You did it. We can move away from it. And the last lab you completed for me last week was on this idea of a potential. So forces can be described explicitly. They also can be derived, if they're conservative, in terms of a potential where the potential is given. So here is 2 objects interacting potentially. You can think about them as 2 comets or 2 asteroids which meet each other. Far away, they don't interact. And then they interact and bend. So you did this lab for me and you all did it very well looking at the marks. Review that, because I could always take this lab or the last assignment and adapt it and do something just like it. Question from the chat. Can you mention how data tables worked again for the different schemes? Which ones are better for different scenarios? So the 3 schemes we talked about are a forward difference, a backward difference, and a centered difference. The forward difference and the backward difference are both first order schemes. It means the error is related to the size of the step in time or in space. Their advantage or disadvantage is you always, for a forward scheme, you always need a value at the current point in time and the next point in time. So if you're trying to evaluate acceleration from velocity data, using a forward difference requires the current velocity and the velocity at whatever the next time step is. What that means is you can't estimate the acceleration for the very last row in your data table because you don't know what the velocity is at the next time. You're at the end of the table. You've got no more answers. Likewise, for the backward difference, you look at the current row, the current velocity, and you compare that to the previous velocity at the previous time step. That would be a scheme that allows you to figure out the acceleration at the very end, but not the acceleration at the very first time, because you would need to know what the velocity was back in time before you start taking any measurements. These 2 schemes are going to give you different numerical answers. They're both have error, but that error is proportional to how small your time step is. A center difference scheme takes a look at what the velocity is both ahead of time and behind in time. And it's a second order scheme, so it's more accurate. But it's not able to tell you anything about the very first acceleration or the very last acceleration. So those are the pros and cons of the different schemes, and there's more of them. Those are just 3. There's a whole family of different schemes out there. They require a different amount of time to process, computational effort. And there are pros and cons. Okay, so that's sort of my summary, I think, of the labs, just sort of narrow it down. And let's just do the same thing for the assignments in terms of which assignment questions I think are worth reviewing again. Assignment question number 1 was a very simple problem. It was just, can you solve the differential equation dy dx equals 2 times x? Okay, it was a very simple thing going, can you just evaluate an Euler algorithm? Well, now that you've done the whole course, maybe you want to go back to this very simple problem and see how you would do it for a Runge-Kutta order 4 algorithm, right? What can you learn about the error of these problems, right? Does this make sense on how to implement this, or for any differential equation? We talked about, I'm going to skip problem B. I would say go ahead and skip that. We talked about the idea of balls falling straight down. The important takeaway here is to understand that the time step is something that you get to choose. One of the things I've seen as I've been reviewing your labs and helping people on this last assignment is you're just picking time steps for whatever. Time steps are your choice. You want to choose as small a time step as you can so the program completes quickly. Better time steps means smaller errors. You'd love to have a tiny time step. The problem is, the smaller your time step, the longer it takes your program to finish. So you can't have a time step being infinitely small. You got to make a choice. One of the things we've learned is whenever you're doing a numerical method, it's very important to check that when you shrink the time step, your answer does not change. Whenever you're doing a simulation, check, verify, test that reducing the time step by, say, a factor of 2 or a factor of 10 doesn't fundamentally change the results. In particular, for assignment 7, depending on what time step you choose, we have 3 particles interacting. If you choose a time step which is too big, the particles are not going to have the right path. Your error is too large. Choose a smaller time step. Always double check that your time step is small enough. And small enough depends upon the problem. You're simulating the lifetime of the cosmos, your time step could be hundreds of millions of years. If you're simulating neurons firing in the brain or some subatomic particle things, you may want to do things in nanoseconds. So the time scale depends upon the problem. I can't tell you what a small time step is going to be. It depends upon the problem. Okay, with that caveat, assignment number 2, we had some examples on how forces depended upon values like y, and how air resistance depended upon the direction. I think those are good assignment questions to at least review your solutions and review my solutions on. Assignment number 3 had some stuff on trajectories of a steel ball and this ping pong ball. I don't think there's anything extra that gets gained by going back to that particular assignment. Don't worry about that one. I would skip it. This idea of investigating how well a numerical method works, like an integration method, that's useful. So here's one where we looked and we compared a rectangular rule to a trapezoid rule, and then we compared how well it worked for another numerical method like compute Simpson. Simpson's rule is not on the final exam, but this idea of running a model, looking at its error as a function of either how many steps you take or the size of the time step, that idea is important. Knowing that the slope of this line, that's really telling you the order of the method. That's another way of interpreting the order, is what's the slope on a log-log plot. Okay. It wouldn't be just a question like this, but this idea of being able to solve a generic mathematical problem using a number of different schemes, that's useful. This could be a problem. This numerical problem could come up from a physics problem. Be able to apply it to midpoint scheme, Euler scheme, or fourth order Runge-Kutta scheme, And I don't have one in mind, but I could give you some other scheme that you have not seen before. For example, predictor corrector you have seen before, so some new scheme, and said, here's the code, here's the algorithm, write code that implements this algorithm. Assignment number 5 was some more worked examples of specific mathematical problems to solve with Runge-Kutta order 4. So it's the same kind of idea all the way through. And again, this concept of the difference between the numerical solution, the exact solution, as a function of time step. Okay? That idea is important to understand. And I'm going to try and include in a final exam question that tests whether or not you understand that changing the time step changes the error, and that tells you something about how the order of the numerical method. Assignment number 6 was a few worked problems in SymPy. Okay, so SymPy was not done incredibly well on test number 2. I might revisit it, so maybe you want to review this again. I might not revisit it, I'm not sure yet, but I could. So here is yet another problem where it's a physical problem where we're defining symbols. We set up an equation, we manipulate it in some way, and you're showing how to solve things, right? So here is an example of a kind of problem we did in assignment 6, and here's another one, and here's another one, right? So this idea of setting up a problem symbolically so that you can apply a solver numerically to it. That's the theme that we're testing. I want to test. And finally, this one which you're working on for me right now that some people have done, forces can be described in terms of potentials if they're conservative forces. That just means that the force is equal to the negative derivative of the potential function. If I put a different kind of potential, it's a different kind of interaction. You're going to get a different kind of behavior to it. And it's just one question on this assignment to finish it up. And as we discussed, Friday noon, Friday 4 p.m. I just want to post the solution. So it's I'll say Friday noon so that I can post the solutions to assignment number 7 Friday afternoon and be done with it. Okay, so I said I've gone through and I've just collected the assignments in the labs, reducing it down. So for the purpose of your studying and review, I would keep with I would focus on what we've covered in assignment in this review lecture, this one, plus these 2 guys. That's sort of all you need to sort of focus on, reducing down everything. Obviously, taking a look at test 1 and test 2 might be helpful. And let's finish off with a little bit of chat on the final exam. Okay, so is that a Monday? I'm going to put a question mark on that because I need to look at a calendar really quickly. Nine. Friday. Sarah, why did you say Friday? Haha. Did you not know we had extra time? The 6th is a Friday. Exam on Monday. Yes. Thank you. All good. Friday, December the 9th. I said I just need to look at a calendar because I didn't know what the date would be up there. So we have that. I believe it's scheduled for a 3-hour 3-hour exam. Okay. Though that would be long in my mind. I hope no one takes 3 hours. In terms of the design, I'm imagining 4 problems. The term test had 3 problems apiece, so the final exam is going to have like 4 problems. So slightly longer than a term test. You have twice as much time for 33% more material. So hopefully that's going to be okay. So far in this course, no one has had to be late for doing the term tests. You all walked out of there in time, but in terms of doing it, that's sort of my scheme. Comprehensive of the whole course. C. I'll say see those 3 notebooks to sort of focus in on what we want to talk about. And it would not hurt to at least take a look at test 1 and test 2, especially if you had problems with an issue all the way through. I have posted what I did for an exam last year. But the important caveat, this is not identical. So if there's something you see in that final exam where you're like, well, we didn't do it this way, that's okay, because it wasn't your course. It was a different version of the course, very similar, but not exactly the same. So take a look at it all the way through. In terms of the style, same idea as the term tests, right? Paper-based, right? We're not going to try and do computers and like that. In terms of aids, they bring 1, 2-sided sheet of notes, hand or typed. Written, I don't really care, but you're more than welcome to bring in things that your brain isn't holding on to. I don't need you to memorize things, but condense it down. So I've already condensed down, oh, good grief, 7 + 7 + 19, whatever that is, into 5 notebooks for yourself. If you're able to take that and reduce it down again to 2 sheets of paper, a front and a back, I think you've covered all the material. I have a question for you though. When I'm preparing this, what I had been doing was similar to the labs, where I gave you a piece of code. So for example, okay, if the question was, okay, so imagine we had some data. Okay, so imagine this was the question. We had done something and we had a data table, and the data table had 3 columns. So we could talk about data.x, and we could talk about data.y, and we could talk about data.t. Imagine you had some data table, right? If what I wanted to do was get you to plot this is just an example, which one would be the fairer way of doing it? Because it doesn't matter to me. I just want to make sure I do it. What I had been doing is I would give you something like this. Okay. Yeah, there we go. That's one way of doing it. And that's another way of doing it. Okay, so there's 2 different ways I could set this up. One is a straight fill in the blank. And so what I'm looking for, right? What I'd be looking for is data.x, data.y, and then if you want to change the symbol, like that. This would be your answer. Okay, fill in the blanks. But one of the things that I'm recognizing is when I write this out, you have to figure out what my brain is thinking. If I say fill in the special line of code that goes right there, would you prefer I leave it more like this so you could just put in the code the way that your brain thinks about it? Some feedback, please. Do you care? Okay, we got 2 people who prefer, okay, 3 people who prefer option 1. Okay, good. I just wanted to make sure that this, okay, thank you. I just want to make sure that this is useful to you and you wouldn't prefer just to have a straight blank line where you can write whatever you want. I don't want anyone to be confused about plot versus plot or something like that. It's just, if you were to type this out, what would you type in? And I'm just examining to make sure that you know that you have to type in data.x and data.y. Now, there is some technical stuff. I expect that you know that the horizontal coordinate comes first and the vertical coordinate comes second. And this is just an example. We could do anything. But I will keep with the fill in the blank. It does make it very straightforward to mark. I'm looking for one thing, or we will have sort of a few short answer questions, probably something to do with error on these kind of ideas. Okay, is there anything else about, because I've got some ideas for this final exam, but I haven't created it yet. Is there anything that you are hoping, not so much that you're hoping to see, but anything that you're hoping to not see? Is there any type of question I asked on a previous term test that you're like going, please do not do that to us because that's horrible? Is there something I should avoid? Okay. I'll be working on this over the weekend and getting that all prepped. The time of the exam is a little bit early. I have no control on the schedule. This is the registrar's office. They assign the time to us. We're stuck. Okay. I believe there is some criticism of SymPy syntax. I understood. SymPy syntax is definitely new. I won't make you give me SymPy syntax. I will ask you to use something that we take the derivative of in SymPy or the integral of in SymPy and use that in a numerical thing. So no SymPy syntax. Done. Deal. I won't make you do that. Okay, that's just fine with me. I think I posted copies of everything I need to post next week. Would you like me to be available? And if so, how? Email's great. For those of you who have reached out to me by email for assignments, I've tried to respond to you as soon as I see that email. And a question session. Okay, so let's do that. Now, remind me, when does your exam schedule start? It's sometime next week. What's the first day of exams? Right, so next Wednesday. So you have Monday and Tuesday are exam times. This exam isn't for a while. What if I suggest that next Friday, would that be useful. So I'll say Zoom review session. Here, Friday, what would that be? December the 4th, 5th, 6th? I think I'm available then. Is that helpful? If I'm online, we'll just do one of these kind of things. If you're around then, drop in. By then, you'll hopefully look through this stuff. It's not the day before the exam, but is that a reasonable time for those who are interested? That would be great. Okay, so I will be online as we have done before. Now, this is something where ideally you're calling into Zoom from home, but I'll post that as an announcement on the course website that that's a review session, and it's really based on questions. So if you've got no questions, that's totally fine. But I will put that in my calendar to log in for an hour and a half or two, a week and a day from there. Okay, so we're nearing the end of the formal lecture period. There's no more labs other than just finishing off that last assignment and me getting you those last few assignments marked. We are done the material for the course. Any other final thoughts? Anything you want to talk about, ask, say? Okay. Thank you all very much. Thank you for accommodating me this term. So far, I'm totally happy where everybody is in the course. I'll prepare a final exam, and I said I am available next week to try and facilitate as much as I can. So thanks all, and I'll see you in person in the exam on Monday, December the 9th. Thanks all.